Hello and welcome to our next Shell Eco Marathon virtual learning session with Altair Engineering. And welcome back to those of you who have joined one of our previous sessions. My name is Norman Koch and I'm the Global General Manager of Shell Eco Marathon. I want to start off by thanking all of you for your flexibility and understanding as we evolve Shell Eco Marathon during the impact of COVID-19. As the situation continues to change, the safety of our Shell Eco Marathon participants, of course, and also our organizing team remains our top priority. Given the current status, we're excited to have you all with us in this new digital environment to kick off our virtual learning session, all from the safety of your homes. Today, you'll be hearing from Paul Over from Altair Engineering about lower energy consumption and better performance with optimized aerodynamics. Altair is a global technology company that provides software and cloud solutions in product development, high-performance computing, and data analytics. Altair has been supporting Shell Eco Marathon by supplying licenses, training, and support for Altair HyperWorks to the teams competing in Shell Eco Marathon for 4 years. Paul is a master's student of theoretical mechanical engineering at Hamburg University of Technology. His focus is on fluid mechanics and aeroacoustics. He led some of the CFD activities for thermal management and race aerodynamics at the Formula student team Ignition in Hamburg. After an internship at Altair in Sweden to create the Ultra Fluid X ebook, he continues to work as student ambassador for Altair. In his free time, believe it or not, he loves fluids as well. He enjoys free diving, fishing, and does other kinds of water sports. So welcome, Paul, and we look forward to hearing from you in a few
Thanks,
moments.
Norman.
Before we get there, just a couple of housekeeping comments. We would like to make this session as interactive as possible. So if you have any questions throughout the presentation, please go to the website menti.com on your browser and enter the code shown on the screen. On Menti, you will be able then to post your questions and see other questions that have been asked and even give them a thumbs up so that the most popular questions rise to the top of the queue. If by any chance you have any issues accessing Menti, you can also post your questions in the YouTube comment box on the right-hand side of the screen when you're logged on to YouTube. Paul from Altair will then be answering your question after the presentation portion at the end of this live stream. And don't forget, this is a live stream, so please bear with us. If we have any technical problems, we will get back to you and we're trying to fix this problem as quickly as we can. That's pretty much all from me for now. I'll hand over now to Paul from Altair, who will officially kick off the session. Paul, the floor is yours.
Thanks, Norman, for this awesome introduction. Guys, this is not the Shell Eco Marathon we all wanted to have, but now we can take this time to go further in development. At this place, a big thank you to Shell to organize this webinar and keep up this platform. The last days, you had the opportunity to have a look into analysis and topology optimization with Altair Inspired. I'm hosted with my colleague Eric. Today, we're going to dive into modern CFD and especially into low energy consumption and better performance with optimized aerodynamics. I just brought some slides with you, and yeah, let's just get started and have a look. What was all combining us in engineering is maybe the motorsport. And motorsport is a world of challenges and a world where automotive companies are continuously under pressure to set new lap time records. They develop and employ new technologies and keep on breaking their own records. Race cars are one big part of it, and race cars are characteristic by highly developed assemblies, engines, chassis, and of course, external and internal aerodynamic characteristics. The same principle yield also for the Shell Eco Marathon. Every year, you guys, the teams, they compete on events in ultra efficiency classes. Besides the drivetrain, the kinematics, and the software, the external aerodynamic design is an essential element to reach ultra efficiency. But yeah, let's wrap it up. Start from the beginning. What is automotive external aerodynamics? The external automotive aerodynamics are mainly influenced or mainly built up by the flow around the car, which directly leads to forces acting on the vehicle. Besides the lateral forces and moments which might be created due to crosswinds, the greatest interest is in lift and drag. Here on the right, indicated in the picture, you see it indicated by these small arrows. The drag, a force which acts against the driving direction, is directly related to fuel consumption, maximum velocity, or the range how long the vehicle can drive in one tank. The lift itself is the force which pushes the vehicle to the ground. It's related to driving stability, cornering behavior, and makes the car smooth and let the car drive quite constant on that. There are two equations below here. They formulate the coefficients belonging to these forces. To compare simulations, coefficients and dimensionless especially are really important. On the left, you have the coefficient of drag. On the right, you have the coefficient of lift. But now back to the ultra efficiency topic. To be ultra efficient, the drag should be therefore considered separately because it determines the fuel consumption as well as the maximum velocity. But where does it originate from? Can those regions be identified? I just prepared a slide to point out some sensitive regions, which are more drag important and which less. In general, 40% of the proportion and the shape determine the drag. The drag is determined by 40% of proportion and shape, 30% of wheelhouse and wheel, and 10% of internal flow, and 20% around the underflow. In respect to that, the Shell Eco Marathon vehicles, probably the most important might be the proportion and shape of the body and the wheels and the wheel housing. So let's take a look on some numbers. Why should we care, especially about external aerodynamics? The EUDC and NEDC and the table, two cycles, they stand for emission test cycles made by the automotive industry. On the left of the slide, you see the characteristics, what aerodynamics really is. But now back to the numbers. Now, if there is all clear, we just dive into it directly. So, in this cycle, when we drive in the city, and now we change the coefficient drag about 0.01, the fuel consumption would change accordingly to that, about 0.01 liters per 100 kilometers. This would relate to a change of vehicle mass about 6 kilograms. Driving now not in the city, or especially on the Autobahn, the German motor highway or something, around 100 kilometers an hour, and changing now the CD about the same amount, 0.01. That would relate to a fuel consumption change about 0.09 liters on 100 kilometers. And now guess the mass is quite high. It's about 129 kilograms equivalent mass, which is related to that. And I think that's quite a lot. Optimizing aerodynamics of a vehicle is quite a difficult task. It requires experience, theoretical knowledge, experimental data, maybe from wind tunnel or simulation, or from modern high-performance computers. All is required to achieve an efficient, balanced, and good aerodynamic setup. Today, my mission is to give you an ultimate insight into lower energy consumption and better performance with optimized aerodynamics. Let's have a look what we're talking about in detail. Like I already said, optimizing the aerodynamics of a vehicle is a difficult task. So we have to take a small look in theory first. That's where we start. I like to dive into some basics to get you all your theoretical knowledge back up and running. Of course, simulation nowadays are an integral part of vehicle development and thus also an integral part of everyday engineering life. So we will dive into some practical part. I'm going to show you some brilliant software which makes it intuitive to set up a simulation for your own Shell Eco Marathon racer. At the end, we will have a look on some results I prepared and talk about common ways to post-process your simulation in an efficient way. After all the session, you should be able to start with your own ultra-fast transient simulation. If you have any question or like to give any comments during the presentation, please use Menti now spotted in below and dial in the code 220330. Ready you go. And in the end, we will try to handle all questions with Norman in the Q&A session. But now, let's just dive into some basics and advices in ground vehicle aerodynamics. Ground vehicle aerodynamics could be split into reality and virtuality. How does the reality look like? So this is not really real. This is more a schematic car sketch, but let's try to understand it. Imagine you're driving on the road and the air in front of you is in totally stationary and totally equilibrium. The car moves towards the air flows around the car. At the front bumper, the air hits the car normal to its surface. The velocity of the air goes to zero and the pressure increases to its local maximum. The air above the front bumper gets pushed up. The velocity rises and the pressure decreases. The effect of suction appears. The same yields for beneath the car. The air gets pressed through the small gap between the vehicle and the ground, and the effect of suction appears as well. Behind the car, the thing looks a little bit different. There we can see flow separation, and flow separation always introduces a lot of drag. That's not only the only thing which can reduce drag. There are some more. But now, let's have a look into reality. Where does the drag come from and how does it really look like? When we take it to a real car, especially here a Shell Eco Marathon racer, it is possible to point out region of interest in more detail. The percentage I given there, they are on the overall drag. Just possible because of an unoptimized design. For example, when we take the radius at the front bumper, it is causing up to 2% of the overall drag. The roof contour here, listed with number 5 in the graphics, has an influence of about 1%. And the diffuser, right at the back, shows nearly no installation drag at all. And when you remember the numbers from the beginning, how much energy you could save and how much further you could drive. Quite a lot. The question is how to save it. And that's what we like to dive into. The underbody is the main part in aerodynamic devices and aerodynamic places which we should keep in mind of. It can be separated in ground clearance, which determines the gap between car and surface, and the pitch, which says if we have a nose up or down car. And of course, underbody covers also help a lot. But let's start at ground clearance or at the pitch first. So increasing the pitch, so getting the nose up a bit, leads to increased drag and lift. A negative pitch, for example, creates a kind of pseudo diffuser effect of the entire underbody. Reduced drag, which is then reducing drag and lift. On the diffuser effect, we're going to have another look on the next slide, but just to point out here what's happening. When we look at the ground clearance, it's similar. The smaller ground clearance, the lower the drag. The lift have to be handled a little bit different. For the lift, there's a kind of optimal ride height for the car where we should have it. When it then comes to the flow underneath the car, it's quite important to have underbody covers to reduce the roughness and therefore reduce the turbulence in the flow, which is then reducing the drag. If it's possible to cover the underbody straight from the front as far down as possible, it's really good. But look out, there might be some full sheeting of the underbody might not be possible due to thermal requirements, cooling air transport, or other constraints. So you should definitely keep an eye on this. Now, I already spoke about the rear diffuser. This is a special device. And the installation drag we already had is close to zero. A well-designed diffuser can help to reduce drag and also lift. In general, it yields that longer diffusers are more efficient. But they only work well for undistributed upstream flows, as found on many of the Shell Eco Marathon vehicles. So that is maybe quite interesting here. This is a device you can easily develop and have to work on, which you then adapt to your car, gives you more without losing any. So have a look on that, keep that in mind. Another big thing on Shell Eco Marathon vehicles is maybe the wheels. They are super important as well. At the wheels, there we have a superposition of the flow around the car and around the wheel. Those two lead to super complex flows, and even the wheel rotation introduce additional effects. Overall, it can be introducing about 30% of the overall drag. So lots of potential for optimization. Where to attack? Tire and rim size could be altered. Maybe a closed wheel setup is more suitable instead of an open wheel one. Do experiments and run simulations to make sure you get all design approaches in your array. Another big thing in Shell Eco Marathon is another point regarding in and outlets of internal flow. How to design these interfaces, especially interesting when it comes to cooling your fuel cells, batteries, or engines. A proper design can save a lot. By using added momentum due to the radiator, it might even be possible to reduce the installation drag close to zero. Let's take a look at some example. I just plotted some examples here on the side. We have 4 options of cars and additional data in bar diagrams below. Version A, a classic passenger vehicle. It has high drag and also quite good mass flow. It's the most common way that the air enters straight in the front in the car and then cools down the engine parts. Option C is a little bit altered. The air is sucked in at the bottom and given out behind the front bumper. But when we now look at bar diagrams, we can see that using pressure regions for support, like in this case, we can achieve a lower drag by the same mass flow. So the conclusion on this one is inlet and exhaust for phase and normal stream direction does not necessarily include low drag values. So experiment around and don't use the most obvious solution. Using pressure regions for support is an awesome beginning to then iterate the solution to an even better result. The same, of course, yields for outlets or exhaust. Generally, they should be placed in low pressure coefficient areas. Attention here, because outlets can increase boundary layer thickness and the likelihood of flow separation on the surface attached, which lead then, we learned, flow separation, even to more drag. Let's have a look on some examples here as well. So again, we have 4 approaches, and on the side, on the right one, there are some drag and pressure numbers. If we have a look at version A, we have a conical sheet metal, and the influence in drag and pressure is medium, I would say. In version D, we have a flush exit, and the influence is way smaller. We have no influence in drag, in pressure, and less influence in drag. And when you set it to the right location, you can improve the momentum transport to the boundary and to the surface to get better attachment. But now we got a good understanding, I think, of the reality. How does it look like when it comes to simulations? Why should we use them, and what are the common methods? That should be this section about. But first of all, why should we use numerical simulation? I think a big point is money. Comparison in wind tunnel. So if we have a wind tunnel, we spend money for prototypes and also for energy and staff and maintenance of this wind tunnel. Quite expensive, right? Especially for you student teams, a big point as well is that there is no wind tunnel at all, or if there is one at the uni, we could use it sometimes, but not all the time. So that's where computational fluid dynamics came into account. It's a flexible and fast alternative to wind tunnel experiments. CFD offers almost unlimited possibilities for analyzing of the flow field. Coupled with the computation power of today's computers, CFD makes it possible to develop more complex aerodynamic components and further increase the performance of a vehicle without building and testing every design in the wind tunnel. Let's have a look what's on the market. So we have the Navier-Stokes approach, which is made now from fluid dynamic classes, and also the Lattice-Boltzmann one, but I just wanted to name the common ones, so we stay with these two. A main difference is how they interpret the continuum. The graphic on the right summarizes those differences really good. Let's go through it a bit. So the Navier-Stokes is a conventional CFD, uses a macro scale interpretation. Means that length scales, as we know them, are derived in millimeters, meters, inches, and feet. And the continuum itself is divided in small cubes. Now coming to the Lattice-Boltzmann, it's a particle-based method using a mesoscale interpretation. The continuum is divided into small particles, and length scales in the region are of the mean free path length, maybe known due to quantum mechanics classes. This mean free path length is the length where it's 100% chance that a particle collides with another particle. To just then end up this zoom into continuum, we also have to call the microscale simulation, where we go even closer and we can cover movements of atoms, but we exclude this in this webinar. In both methods, we call a finite volume approach is often used to specially discretize the continuum. And if we take now the comparison from theoretical view to practical ones, there are also some advantages which come into account and might be quite interesting. In a direct comparison of the methods, both can be used, first of all, to describe external aerodynamics. The Lattice-Boltzmann method is transient and explicit. The Navier-Stokes one is implicit and mostly steady state. To have a method which is transient and explicit like Lattice-Boltzmann, we gain way more accuracy, which makes it possible to design aerodynamic more exact. Especially when it comes to high-end efficiency, then this is really a big advantage. They are that accurate and efficient that it's even possible to take a look at aeroacoustic directly from the source data. In Navier-Stokes, all transient information are averaged and summed up into one single shot. So we can't really capture all effects like we saw on that wheel with all the vortices and these transient effects. When it comes to measures, there are also quite some differences shown in this image below I brought here. So when we, on the left side, look for the surface mesh in Lattice-Boltzmann, we see that we have low surface mesh requirements because this is an STL mesh. Yeah. So we don't need to spend that much time. On the right side, in Navier-Stokes, we have high surface mesh requirements, high quality trias. We see around the edges, they get really fine and it's placed everything really organized. The volume mesh looks similar. So we have on one side, Lattice-Boltzmann, a finite volume method with a pure Cartesian grid, which is generated automatically by the solver. In Navier-Stokes, we have a finite volume approach, which is locally adapted grid then. So there we have to adapt it to every complex geometry to make sure that it's nice and connected. But also a big part when we're comparing it for a transient simulation should be the runtime. In Lattice-Boltzmann, we take half a day, and for the same case, we would need easily 2 days in Navier-Stokes, so a quarter of the overall time. This allows us to get way faster turnaround times and adapt to design changes. Now you're probably all thinking about, what is this Lattice-Boltzmann method? Okay, let's have a look in detail. We have an equation, the Boltzmann equation. I'm going to show it on the next slide. But first of all, imagine that equation is now solved on a discrete lattice. This lattice is constructed out of voxels, like this one on the right up here. Now, the solving step is separated in 2 steps, the streaming step and the collusion step. Particle stream in the determined direction. Then the particles collide. New velocities get computed. And there we discretize. The only possible particle velocities are just 19 ones, because we use a D3Q19 velocity set. And that's the only place where we discretize the time and space in the same time. So we just allow 19 possible velocities for these particles, so they can move but not totally free. Due to this discretization, the transient nature of the flow is inherently respected, and the physical behavior is determined by the viscosity of the fluid. When, for example, it comes to errors in your simulation, the errors are mostly not of numerical nature. It's more about physical nature, because you enter or you introduce some mass or momentum at a place where it can't be integrated. Now, at last, have some small look onto the iteration process in detail, and then we close up this theory part. But I think it's quite important to have a last look on the Boltzmann equation and how it works. So the Boltzmann equation is up the right one in the middle. It sets recent and equilibrium density of particles into relation. Then, from the collusion and streaming step, we always determine the new velocities and the new densities. And then, based on all this and all the Boltzmann equation, we can compute macroscopic moments like velocity, density, or pressure. So from these solutions, we can cover up the solutions of the Navier-Stokes solver. Lattice-Boltzmann equation solution imply the solution of Navier-Stokes. And that's really good and interesting part here. Okay, we summarize that up. So we have low surface mesh requirements. The volume meshing is nearly trivial, and we can have transient simulation, which should be more interesting in regard to high efficient external aerodynamics. I think it was quite a lot of theoretical input here, and we just want to close this up. So if you have any question or had any question during the last slides or the next slides, please use menti.com, dial in the code 2203, and then put in the question there. You can vote others up and interact there a little bit, and then we will try to handle all questions in the end with Norm in the small Q&A session there. Besides this, I already can point out that we published an ebook which summarizes all this theory and will give you some more information and a deeper look into theory, into Boltzmann equation. So don't hurry, we come to this later. Now we have enough with theoretical background, I would say. So let's see how the things really work. Every simulation progress has a similar simulation pipeline or a setup, and you can break it down in this general way. We have the preparation step where the surface is prepared, and we will do that today in the practical part in Inspire Studio. The pre-processing, the setup of the simulation, we will do in virtual wind tunnel. The solving part, we will do in Ultra, and the last, the post-processing, the result, analyzing, and all this we will do in AccuField. So what are the tools about? Inspire Studio is from design to manufacture, all in a single easy-to-use platform. It's really intuitive to learn and easy to use. We can do free-form shapes and continuous NURBS geometry. I like it a lot when it comes to wings or all this, because sometimes it's quite hard to get smooth round edges by normal cut tools. And here in Inspire, you can easily do it with NURBS geometry. We have some powerful sketching environment to create CD sketch curves, and of course, we can discretize surfaces, which then leads, when you save it and export it, to a smooth transition to virtual wind tunnel. Virtual wind tunnel is the pre-processing tool. Altair's virtual wind tunnel is a vertical application tailored for external aerodynamic studies. Designed with the user's needs in mind, the graphical user interface provides easy access to problem and definition and solution strategies. The automated and customer-label report generation after each simulation runs provides a consistent method for design evaluation. Everything up there is organized in a streamlined way that you can just go through ribbons and menus and easily get to the point where you will export the simulation to UltraFluidX. UltraFluidX is the heart of all this pipeline. It's a simulation tool for the prediction of external aerodynamics and properties. The technology is based on the Lefitz-Boltzmann method, which allows us to have transient solution, ultra-fast solutions, which leads to small turnaround times. The code is optimized for GPUs to deliver extreme performance. When the simulation has done finished, we can export those files into AccuField View, which is the post-processing software for CFD simulations. We could either have a quantitative analysis by generating plots and diagrams and have a look into the boundary layers, or we could do a visual analysis. Vector scenes and scalar animations are no problem at all. If you want to have a little bit more fun, and maybe that's good also when you do some slides, we have a rendering with backgrounds and materials, like I did here for the Roadster. Okay, now you just know all the software we want to use. So let's have a look inside and see what's it feel like to use these programs. So right here, we can switch into Inspire Studio. I just opened that one up on my desktop, and we will have a look onto some nice geometry. You already see here in the have a look picture now I think we are able to start here in Inspire Studio to move around a bit and get comfy with ourselves. I already loaded up a model, which is now the Terraphanic from TU Graz, and they just sent the model. It's really nice to have it here for presentation. So as I said, I loaded up the model, and now we like to introduce to some ribbons up here. First of all, it's good to call out the option. So if you have a left mouse click, you can just easily select things. Like here, I select the model which is popping up here now. The mouse wheel is needed for zooming. When you press it, you can rotate around center of gravity. And the right click, it's translation in the display plane. So quite easy handling, I would say. Up here is a measure box. If you like to check some dimensions or the move thing, we can also have a look at this. But I think we should be fine in movement right now. Therefore, I like to just have a look onto curve and geometry interpretation. You have to know that Inspire Studio is more a design tool, which offers like the polynorbs options. And it's not a CAD software, so it should go hand in hand. It offers a lot of more creativity and design approaches than a CAD software. So it's just, maybe a good or an awesome add-on, I would say. And for aerodynamics, it's nice because you can, first of all, just have easy design what you make. You don't have to bother around with these CAD option limited spaces and functionalities. So let's have a go through. We would like to draw a curve on a surface. If we like to, maybe I thought about let's do a hatch up here or lookout where the driver, I think it's now laying in these Shell Echo Marathon Racer. So we like to give it a little bit more upright position that he can look on the road. So therefore, we just click here on this blue polynobs line to adapt it. Maybe I change to the top view for this, and then we can easily just plug in the curve what we like to create. You see now, and when I just finish it up here, then we get to a curve. Of course, I prepared already some, which could look like this. I spent some time into aerodynamic, kind of shaping. But this curve is now only on one side of the vehicle. To get the other one to really close that curve, we could easily just walk through here a little bit, and we were looking for symmetry options, I would say. So maybe modify could be a thing, and when we then scroll further, here we see some symmetry, planar symmetry. Oh, we click that sounds suitable. Now we can easily just click on the curve on surface, click there, and now we could use those options, or we just select another identities up here to make it clear what we like to have mirrored on the other side. I like to mirror on Y plane to get it like this. When we see now at the top, you see that's totally the other way around we would love to have it around here. So we can click on this blue dot here and now enter the dimension what we're thinking about. Here I have to point out it's not necessary to use the metric system. For me, it's quite handy, but especially you could also easily enter 10-inch like this, and then it would transfer it directly into millimeters, so you don't have to use calculator or Google. I think it's quite a good add-on or gadget. So, but now we like to have it right in the middle. So I press 0. It doesn't matter if inches or millimeters, but we want to have it there. Now we just confirm this up here and ready to go. We have the curve. Now the idea would be to extend it up a bit, that the driver can sit into that and have his head up there. So we like to extrude something. So maybe here, there's an extrude under surfaces and extrude for surfacing. So that means here we can really interact with surface. These are some primitive ones. Here we have the extend ones. So we click on extrude. So object select one or more curves on surfaces and click confirm. Okay, we do that. I think it's also quite nice that it always gives a little bit advices on this. So for example, here we have curve on surface now popping up. We click that. Ooh, got it. Click that. Got it. Here also the height is displayed. You can use here, like you can click here with the mouse and then go left and right to make it high or low. It's quite easy, I would say. If we now have a look from the front, we see that's not even. So I would say we just make it even to global axis, to y-axis, and that's where sometimes I have a problem at. Give me a sec. We can easily not invert direction. No, stop that. We just have a look again on that tool. So we want to have a reference direction as the rail, and now we get the objects selected, like this one and this one, and doesn't do this really. Right now, I think my laptop is a little bit stuck in there. Once again, yeah, there we are. There we are. That looks good. So we got this one prepared. Great. Now we could easily close this option up here, and then we would have our new volume. So what to choose there are here. We got on the surface and patch. Now we just click here, select the boundary curves or surface edges. We click on that. Oh, close. Awesome. Let's take that. Now it's only needed to mesh these things. For meshing, we go on poly NURBS and then continue to NURBS to poly. If you click this option, the mesh process will start. I just prepared a good tessellation. I'm going to show you this right now. This was my presentation I derived the last days, and I went for a really coarse and triangular mesh here. So if you got the model changed as you liked, then you could easily just click up here on File and then Export or Save. For me, it's not possible right now because I haven't meshed these big bodies here. So that's why the option is now, now it's available. Okay, maybe I have selected some. So you go on Save, and then it will save all this. But now the only thing we could run in Ultra would be that hatch, so we had to mesh that first. I already prepared that, surprise, and loaded it already into Ultra, into Virtual Wind Tunnel, I mean. You can just load it in by import and then select the file you want to have, and then it should be listed up this way. Like I already said, Virtual Wind Tunnel shows a more streamlined version. So we start right here, and when we end up here in the end, we set up the simulation. Quite easy. Again, the typical Altair options up here to move, to scale, to measure. Always quite handy when it comes to designing and all these things. So let's start at that. First of all, we need to make sure that all the parts are here, but I think none is missing. So let's generate, or maybe now I like to first point out there are some favorite settings you should choose or select. I think the model browser, I ticked it here, and the property browser and the view option. These are really good because this gives you a good overview where you can then don't have to click all the parts to see the properties. It shows you automatically, especially when it comes to dimension of refinements and all this. It's nice to have. So another thing maybe is to first to check if, or maybe we do the wind tunnel first. So doing the wind tunnel, we now see that we already got assigned some dimensions, all this. Now it's time for me always to just click that we get right into the tunnel, that nothing is lurking around. And here we see that the tires are intersecting a little, so that's quite good. Should be a kind of deformed tire, but we would like to have it like this. If it not been like this, maybe the car would be split in half by the tunnel's ground. Then you would use the move function to move the vehicle. Now it's interesting to set those dimensions. For setting the inflow velocity, just double click on this arrow, and now the inflow velocity is popping up. For me, I prefer to enter kilometers per hour, but there you could also enter something else. It automatically transfers the number into the units where you are at. And right now we are in MKS, that means that we are meters, kilograms, and seconds. The dimension of those wind tunnels we'll leave for the moment like this. I think they're quite good in the beginning. And then here, when you click on that symbol, you can just undisplay it, that we can work with the model a little bit better. The next part up here would be to have the identified part ribbon. So identifying part is really important to let Ultra know what kind of part it is. If it is a heat exchanger or a tire or a normal body part. So this one is a normal body part. But we also have some tires. There we have the normal wheels and some multi-reference frame zones, which I come later to. So we just click the normal wheels here. Then we can flip the model upside down by using the mouse wheel, and then we can just select these tires by clicking on them. Now they show up in red. This makes sure that we have selected them right. Another thing which changes is here, we get the tire symbol. What's really nice and handy, I would say, as a user, is that with the wind tunnel computes the rotational speeds of that tires automatically. So if we look now here into the property editor, we get a huge list where we have auto calculation for the RPM takes. So we get 430 rounds per minute, which is corresponding to 11.1 meter per second driving speed. What's also really important is for Ultra is to check the normals. The normals are determined, the normals of the surface determine directly where Ultra places the fluid and how the program handles the geometry. So by clicking normals and seeing location, the body, we see that we are outward turn normals, which indicates that everything is right here. If they were inward, you can click unify all here. So coming to the mesh option, the far field voxel is set on 0.2 meters, which is quite good for those setups. And now it's not it's not finer to the surface, which should be to really get a good resolution. So therefore we could use some box refinement, and we click the box, and then after this directly body, and you see there it is, we got our refinement. Refinement level would be 1 to have a smooth transition between refinement level 0, the far field, and 1, the next high one. There are also offset regions possible, or small boxes around one part, or even custom ones, which you can import from Inspire Studio. But beside from that, there's a really cool function I like to show you guys. This is the mesh import function. So therefore, I will delete this box, what we just made here, and click on File, and then Import. No, not import, template it's called, sorry. Template, and there we can import a full simulation setting file in case we already run few simulation from that type and we just want to have a design so that we don't need to set up the simulation every time on our own. So import the full simulation. There's already an XML file what it takes to import, and there we are. We got all the mesh controls, the coordinate system, and everything assigned to this new simulation setup. Okay, now we just need to get the material clear. Here we have standard air as a default material in our library. If you have any wind tunnel validation or something, you could add your material under My Materials to make sure that density and viscosity of the air are matched perfectly. And if you have some belt system in the wind tunnel, you could add them here as well. After we are finished that row, as I said, we just click on Run. Now we can set some last things. Here the runtime gets set and some other things which should be reorganized, but I come to them in the next slide to give you some more guidance there. You just click on Export and then you're able to load it up to the cluster to have a look and run the simulation and then have a look into the results. That's what we're going to do right now as well. We're going to hit back into the slides, and I prepared some guides for you. You could have a look at and may need to set up your own first simulation. So let's quickly summarize this, and then we hit to the analytics and results section. So setting up a CFD, I like to just summarize some key facts. Regarding this surface mesh, we only need triangle elements, just trios. The element quality is of low importance. Part intersection, like in the tire ground one, is allowed. But the only big thing is that surface normals must point outwards. And a recommended setting is that the mesh should be closed and watertight. But if there are some small cracks due to CAD problems, it doesn't matter. For ultra, it normally catches that. Coming now to the computational domain. First of all, it's important to understand that voxel size and number of iteration determine the computational time significantly. In general, 30 to 50 flow passes are suitable to reach convergence in automotive setups. One flow pass refers to the time it takes for a single fluid particle to completely stream over the entire body of the car. The coarsest mesh size, that one in the far field in the wind tunnel, is common to have around 0.05 to 0.2 meters. 0.2 meters we had in our case in the wind tunnel. My personal best number is 0.192. It's a good number to choose, and you figure out why when you did some simulation and had a look at. The domain should show kind of blocking ratio of around 0.1%. That means that the projected area of the vehicle in flow direction divided by the area of the inflow section of the wind tunnel should be in 0.1% relation. On the right here, there is a graphic which gives the dimensions of such a wind tunnel in respect to vehicle dimensions. And I thought to make it easy for you to adapt them, it's quite nice to have it here. You see that the numbers before and after the car in flow direction are slightly different. And those we also going to see again in the next slide. So remember this kind of setting. Finishing now up the far field from a relative coarse Cartesian background grid, the mesh is consecutively refined to fall towards the surface. The outer levels are typically defined via box like we already saw with this rectangular shape. And of course, there are some guidelines as well to get some guidance and advices. Talking about rectangular refinements, it is made from first interest to know what we like to achieve. So we like to achieve around 3 to 6 millimeters at the boundary of the car geometry. Usually, it spans around 8 refinement levels from 0 to 7 to get there. The guidelines here in the list I wrote give you some variables to iterate. Again, the first number is in x direction, so in vehicle's length with the L, the first number is the distance from the vehicle's center of gravity to the inlet, and if there is a bracket, then that is the number from the vehicle's center of gravity to the outlet. If there's just not one number given, that's the overall length, which is then symmetrically to the center of gravity of the vehicle. But attention, when you iterate those values, then you should keep in mind it costs a computational power. Time stepping on the refinement level 0 yields to an adequate sub-time stepping in refinement zones. That means that having one time step performed on refinement level 0, you have to perform 2 time steps on refinement level 1. So if you do 1 time step on refinement level 0, it's already 4 time steps on refinement level 2. And now you imagine it's kind of to the power of 2 thing. The 2 to the power of something thing. So this is because we use an oak tree based 2-to-1 refinement technique. But I just want to make you sensitive for the cost of these refinements and also to high refinement numbers. If we come closer and closer to the surface, we need a little bit more higher refinement, like this one here in the table. We have refinement level 5, so we have 6 different voxel sizes now. We could spend 2 more to end up at these 8 I initially said. We could use them either based on geometry or definite custom volumes, like we already saw in the virtual wind tunnel practical session. When we use part-based refinement, here the whole body in the left shows the high stresses. It's good to look at those ones. The conclusion here is that we have high stresses on the wheelhouse and on the top. So it would be nice to use a part-based refinement on the whole body. Those regions with high stress are regions where turbulence appears close to the body. They show a high transient character, so it may be suitable to get a little bit more resolution. The picture on the left side shows the transition from the coarse mesh right at the top, rectangularly placed, to the fine mesh wrap around the body. Instead of defining these wraps, we also could use a custom volume as well. The predefined volume refinement zones can adapt to similar geometry by using morphing in Inspire Studio, which takes us back to preparation of the model, where we have to introduce these custom zones, like this one here on the mirror lighted up in orange of the Roadster. Another idea would be to, like the animation, the lower one, to have a custom refinement around the wheels. The region can be extended to fit the whole tire rake in a refined way. And in the end, we can then gain more accurate results. While talking about tires, it might also be suitable or even logical to call out an additional improvement we can do. So outstanding wheels, like often saw on Shell Eco Marathon vehicles, should be analyzed a bit more in detail because it's about high efficiency. Then you could use, if you're interested, you could use Altair radials to create deformed tires. And then overall, you get your aerodynamic, of course, more efficient by better reality approximation. I think it was, again, a lot of input for you guys and a lot of numbers to think about when it comes to simulations and what we should do and how to place these things. If you have any questions or need guidance in setting up, or now there's something coming up, you should please use menti.com to dial in the code 220330. And then we are ready to go. We will try to handle all questions regarding the setup later with Norman back in the Shell studio in a question and answer session. Beside there, this is already all published in the ebook, which is available. It covers all of these guides and shows them even more detailed. As well, this recording will be online so that you come back and then just pause the slide when you're setting up your own simulation and take it as a step-by-step help on that side. But now coming back to the results and the last main interesting part, I think, to have a look on really some hands-on Shell Echo Marathon vehicle we got. So I just run two cases. I got an initial case of the Terrafanic already, which you already know, and then I got my custom case. My ideas were to have a flat front bumper to add a cooling inlet for a battery or fuel cell or even an engine. And then the idea we already had in the practical session to have a look out a hatch or something for the driver to have a better overview on the track. How does the result look like? Let's have a look on that. So let's dive into the analytics. First of all, I think you should always have a look on the computational time. As I already said, UltraFluid X needs GPUs to run. There are some older K80 graphic cards and some newer V100 graphic cards. On the older resources, the case runs around 12 hours. On the newer ones, it takes not even an hour to finish that transient simulation. And in both cases, Ultra's implementation achieves the same coefficient and so the same result quality. Now, beside the computational time, you should also look at the progression of the forces, or even especially the coefficients, to make sure that the simulation went good and calm. Numerically wise, of course. I think the storm in the wind tunnel is not calm, but the coefficient should look calm. But yeah, when you look at those diagrams, you see that we have a launching up session at the beginning where the flow gets accelerated from 0 to 11 meters per second. The transition peak, what we see there, the small jump, is where the flow turns from laminar to turbulent flow. It can be spotted quite good in here, I think. Now, when we see at the drag, the upper black one diagram, we see that the drag is after that nearly constant. The lift is a little bit more fluctuating around the mean, but in general, I say the conclusion here is the simulation is worse to post-process. That's always these two steps what I do when I do simulation. I really have a look how the simulation performed. So let's have a look on the results. Taking the average low-pass filtering the last iterations, we get some CD and CL values. Comparing the original case and the custom case down in the table, we see that the coefficient of drag differs about 0.023, and this coefficient of lift differs about 0.354. Now taking a look on these nice animations of the transient flow outputted by Ultra, we see that we have compared the lower custom case with the upper one, a way lower velocity or bigger area with low velocity in the front. As well as the roof contour, after the hatch, the flow gets totally turbulent and detached. We can now point out that maybe the front bumper and the roof contour have some negative influences on these results and therefore change the coefficient. To confirm that, let's have a look on some more quantitative tools. For example, the sectional drag. On sectional drag, the vehicle gets slides up into 100 sections. For each section, drag and lift get computed. And then I just plotted them, every value of these 100 ones in these diagrams above. On the left, you see the custom case. On the right, there's again, on the right, there's the custom case, of course. On the left, the original, the initial one. You can spot directly that we have an influence at the drag at the front bumper due to the jump directly, the red one on the right side. As well, it is also can be spotted at this kind of hatch lookout thing. There's also a big bubble coming up in blue, which is indicating additional lift. Another way to look at these results quantitatively would be to look at the cumulate, the drag, and the lift per section. There we sum up all the values of the slices when we pass those slices. Now it's important to look for strong gradients which indicate major influences. For example, in the right custom case, we have a huge gradient directly at this lookout hatch thing. Also, we can see that the lift value is just exploding through the ceiling and never seen again. And I think this is made that changes of the roof contour, they apply these huge lift changes. But now we're on the base that we are still don't know which part actually changes the flow that strongly. So maybe we can have a look at another tool to confirm that the body changes I perform haven't been that suitable. And therefore, we can look at the drag per part. And we've seen now that the body has gained new influence. From 90 to 91 is, of course, an increase, and therefore maybe not the best we like to have. So, lessons learned. What do we know? Maybe my design was not the suitable one, but therefore it's a design iteration, and we should now take the conclusion to go back to the last step. A flat front bumper is not optimal. We like to have it streamlined at the front. That's maybe the idea. And the lying drive position allows and even supports this streamlined design. When we then I had an idea to, when we looked at these wheel housings, I saw that they might be a little bit more draggy than the body itself. So why don't you do bioengineering a little bit? The Hamburg wheel here in the graphic below, it has some tubercles kind of on his front wings, on his front wings. And my idea was to create them on these wheel houses to decrease the drag. So that could be tested and running just a new design cycle. And I think why not? Why not to test it out? There's just one thing I finally you should definitely take home with you beside all this information that I really want to make clear. Learn from the tests you made, learn from the iterations you take. This iteration was still giving us some new backgrounds, informations, and now we can improve and try new concept and design. If we try that Hamburg thing and it works, awesome. If not, we know that we should maybe go back to more scientific ideas. And another point is use the post-processing techniques I showed. Do not trust in nice, colorful pictures, and especially use some quantitative results or some quantitative analysis. There you can only trust the numbers, and it's sometimes easier instead of these huge informationally packed images, which there are out there. Looking out of the tools, is there also something what we can summarize and maybe learn from today's session? Of course there are. We have first short preparation time for the surface mesh, completely automated volume meshing, we can perform transient and aerodynamic simulation, and the quick design changes and simple workflow are possible with the intuitive GUI and these tailor-made tools, which really convince. And you can adapt to all trends. You have that fast turnaround times that you easily can run through everything. Summarizing, this is just, I wanted to say that they are easy to use and you save a lot of time with these products. And I know from my former student days that there are some times where time is the most valuable good in project management in the whole project, because then you want to get the car ready in time for the next big event, what we're hopefully going to have next year again. Now we just have to close one session. The question, how to get started. So therefore, as already announced, we published the ebook which summarizes all content you heard in the last hour. Download it. It gives more theoretical and practical advices and guides you through the first steps and let you dive into the topic of ultrafluidics. Sign up at Altair University, download that ebook, also sign up for the Altair Student Edition or apply for sponsorship to get even unlimited access to the software. The last point missing is where to run these cases. Therefore, get in contact with us on Altair University at altair.com. We are working on getting a benchmark GPU to run several test cases and reach out to your regional team as soon as possible. Maybe another point or idea from my side, there are also universities out there who setting up GPUs. Please contact your professor, check the situation at your university, and maybe there is an option available. Last but not least, there is a big thank which should go out to the Shell Echo Marathon team from TU Graz and the Super Mileage team from Duke University for sending in their racer geometries and make it possible to show these hand-on cases, you guys. From my side, a big thank you for you to listen, and it was a pleasure. Let's hit the Q&A session with Norman, and I hand back into the Shell studio.
Yeah, thanks very much, Paul. The Shell studio, which is my home. But then again, that's a very nice description of it. Thank you very much, presentation. I really appreciate it for taking us through the science and the hands-on experience with the software. That's very much appreciated. And we have a lot of questions coming in. So if you have been listening so far and forgotten to type your questions, please don't hesitate. We still have plenty of time. I'll hope we'll run through all of the questions. So if you want to ask any tough questions or something you always wanted to know about aerodynamics and computational flow dynamics, please type in your questions to menti.com. You find the passcode on the screen, or if you have any struggle with Menti, please put them into the comment box on the side of this live stream. Let's dive right into it. And one of the first questions, and probably relevant for everybody working with CFD, how do you verify CFD results? Do they have to be verified experimentally?
That's a good question. So when a company publishes or advises an CFD code which is able to download or buy as program, they always run validation cases. There are some general ones out there, and of course Ultra has been validated, but there are also validation inside maybe a Shell Echo Marathon team. Back in the days, we also had these validations in our Formula student team, where we've been able to go to the wind tunnel, and then we started to use Prandtl tubes to check some pressure at different locations, and to, of course, record the overall drag and lift. Those values we then took to ultrafluid X and run a kind of similar setup there. Of course, it was not the wind tunnel, but we tried to keep us edge as same as possible to that. And then we tried to, then we had a look on these values and looked if we are close to reality and really started to validate our simulation progress and simulation chain. You should definitely have a look on that when you're able. Yeah.
Yeah. So experiments are always the ultimate proof. That is certainly true. Do you have any tips how to keep the flow attached longer?
Yeah, that's a big question and maybe a little bit too general. The thing is, when we thinking about what is the problem that air start to detach and maybe to separate, often the problem is that the boundary layer is getting thicker and thicker. So that layer where the particles get kind of stuck to the wall. And there's the problem that the boundary itself, the car, and when you blow at the car is standing, has zero velocity, and the air you blow has a higher velocity. So the particles at the air can like transfer the movement a little bit, but after a time, the air close to boundaries exhausts kind of because there is not enough energy to still stuck on that car geometry. And then, of course, the layer detaches and then the turbulence transports more momentum through the boundary layer. So if you have a long plate and then you have an exhaust or something and blow on even more into the boundary layer, then it gets bigger, then it probably detaches. So what you need is you need to keep a highly momentum charged boundary layer that you can have it attached the full time. And that's really the problem what a lot of CFD one big CFD problem for all the teams in Shell Echo Marathon, I would guess, that to keep the flow attached that wisely and that good and that perfect. Yeah.
Okay. Another question come in about how does the mesh affect the results of the simulation?
That's a good point. The mesh is mainly affecting these results, but also you have to look out for the computational power you have. Of course, the best result you probably get by using the highest resolution you could get, but those resources are quite limited. So what we have here in Ultra, we have a tool which, when you just take some moderate meshing, you already get a lot out of it due to the Lattice-Boltzmann equation and due to how it handles all the computation. So that is the really nice thing in Ultra. And of course, I would recommend you, if you have the possibility to use a lot performance or have a lot of hardware, then I would recommend you to use a finer mesh. First of all, it's maybe a good way to start with the iterations or the numbers I gave in the presentation and then iterate even higher and higher. Maybe introduce another refine level, and then you probably get a little bit finer results. And then you have to choose if they are accurate enough for you or not. Yeah.
Mm-hmm. Okay, so adjusted to your computing power, basically. No, you cannot do better than your computer does for you.
Yeah.
Another question, can I do steady state with LBM as well?
Of course you can. We already had that small discussion in the last webinar. There's data output in ultrafluid X, which can, and there's a like kind of average value. You can set in how many iterations it takes to average the results you have. So it's kind of low pass filter. If you set that low pass filter ultra high so that over all iterations you are averaging, then you get especially to that steady state solution. And the good thing now is when you have that steady state solution, you still also have the transient one. So if you wonder in the steady state one, why do I have these pressure artifacts here? Then you can go back into the transient solution and have a confirming look.
Okay, thank you. And coming back to some more technical questions that people have been asking. The first one is, will this PowerPoint presentation be made available? Well, I can answer this for you. The presentation as well as the recording will be made available. So if you have all registered, and you will receive when you registered a link to the YouTube video of the recording. And please, by all means, watch it as often as you like, and of course, share it with your teammates and at your university with anybody who would like to learn about CFD and aerodynamic modeling. Also, you mentioned it briefly before, Paul, but will the ebook, when will the published ebook that you mentioned be made available?
Oh, yeah, it is already available. Maybe we can have a look through the Altair University page, where I could also point out where to apply for scholarship, where to get the free student edition. I think my screen is already up. So first of all, maybe about the ebook. We can, up here is a learning library and students and teachers. So first of all, we click on students, then we can just look through. Here we got the free ebook session and here the student competition session. Let's dive into the ebook session first. When we click on ebook, we got on this page. These are all the ebooks published by Altair for you to learn the programs a little bit more deeply and get pulled into that. So here you have the series of Learn External Aerodynamics with Virtual Wind Tunnel and also Learn Aerodynamic Analysis of Automobiles with Altair Ultra Fluid X. And this here is the ebook what I'm talking about, and you easily can click here and then you just scroll down. Here's a small introduction, and then you enter your name, your university, and then you request the book. And that's all for free. And you get downloaded, and you get a link to download in PDF, and that's really helpful. Okay, coming back onto the altairuniversity.com page, you can click here on free student edition, or you go on student and then on student competitions down here, and here can you request scholarship to make sure that you get unlimited access to all the tools we have. Yeah, I think that's quite all. Also, here are some nice other features like online courses and stuff. So click around on that page. I think it's really helpful when you learn all these products.
Okay, and another question specific to the software: is Ultra Fluid X supported on Windows?
That's a good point, because I always ask that myself as well. And the fact is that Ultra Fluid X is only possible to run on Linux or Red Hat systems. Like the most high performance computers are. Your local Windows machine are not able to run Ultra in that way. So no.
Okay, thank you. And now back to the application itself. Can you talk about the advantages and disadvantages of different cell geometries?
Wow. Okay, that's going on deep topic. So I can try to just point out a few things when it comes to quad elements and tria elements. For example, in FE modeling, the tria elements are a little bit more stiffer than the quad elements. When you do a crash test, in that case, you would prefer a tria element than a quad one to be a little bit over predicted, I would say. No, yeah, you would choose a quad element instead of a tria to be a little bit under-predicted, because in the crash test you would make sure that nothing happens. In sense of CFD is a little bit more difficult. Mainly, it is represented by the kind of meshing approach you're going at. So, of course, when you have polygonal meshes, you can adapt to complex geometries, but you have to transform every time all the state variables and process variables back into the global coordinate system. That makes it expensive. In Ultra, we are all in one coordinate system, or it's all the axes are mainly aligned or parallel to each other. That makes it easy on that point. If you'd like to have more information, please write an email to Altair University at altair.com. Then we can figure out some more deeper information about your question.
Okay, and one of our viewers is asking, what's your preferred metric for determining mesh quality?
Okay, that's a good point. There, I think I have to. Oh no, there's a good one. Yeah. So if you like normally in run and like Navier-Stokes approaches, a good metric to determine mesh quality, and especially a good key numbers close to the boundary, are Y plus values. Well, this now really gets into topic. So Y plus values, and Y plus values in Navier-Stokes simulation, especially when it comes to transient simulation, should be around a Y plus value of 1. Due to the fact that Ultra is particle-based and the refinements are costing quite a lot, we get down with the refinements to Y plus values of around 100. But in this sense of Ultra, we don't really can scale on these Y plus values because it's a totally different approach than Navier-Stokes. And still, and additionally to that, we also have a wall model and a turbulence model, which handles especially this transition between the mesh and enclosed vicinity to the boundary itself. Also, I have to point out here again, if you have need more information about your question, then please email Altair University at altair.com, because I need to prepare a little bit. I maybe have to read through some material to really give you more details. Thanks for that
Thanks
question.
very much. It's good to know
Yeah.
how we can reach out for more information. Altair University at altair.com. Do you have any thoughts on what are the advantages of using virtual wind tunnel over AccuConsole?
Oh, yeah. Now you just brought up those two approaches. AccuConsole, also a product developed by Altair, close to AccuSolve. I think it's the main console regarding that. But yeah, it's based on the Navier-Stokes approach, has different kind of simulation techniques in there, like Reynolds average one, detached eddy large vortex structure one, and these are all count into the Navier-Stokes department. Ultra is a different solution. It's in the Lattice-Boltzmann department. So the advantage we called out in these slides, they are especially like showing the differences between those two approaches. So maybe you just download the ebook, have a read through this, or you just watch this webinar again to make sure. And I think then it should be all clear what's the main advantages. As well, there's also the ebook for AccuSolve online, like we showed on the website. Have a look there. Then you can compare them on your own easily and have all details summed up. Yeah.
Okay. And one of our viewers is asking, can you share the simulation settings, the preset ones?
The preset ones. At the moment, I think you should definitely contact us under altairuniversity.com. Now at Altair University at altair.com at the email to make sure that we can send them to you or figure that out. I think these are exactly the settings I used in the ebook as well. So these are quite these are written down there, and then you can just adapt it. And but if not, please contact us.
Coming back to the previous questions, just to build on that, should I use AccuSolve or UltraFluidX for thermal simulation?
You should definitely use AccuSolve for this. UltraFluidX is only capable to calculate external aerodynamics, and AccuSolve on the other side is Navier-Stokes based, so it can easily, with an additional transport equation, also solve thermal problems.
Okay. How did you calculate the shape of the deformed tires?
I did do it in a practical way by just using the Altair radius. So we can have a look back on that slide. I just tried to get that one up, and then we can have some more informations. So it should pop up now. We have Altair, the structural solver radius can be utilized to create the deformed tires, like, for example, on all of these Shell Echo Marathon vehicles. Therefore, please also go on the Altair University webpage and just click through to radios. There should be some guides which guide you through, and with the sponsoring or the student edition, you of course get the access to that tools that you can create them on your own. But I think that's a really high-end topic. You should be clear that if it's really necessary to use it, then you should also think about to use the MRF approach and really get to high resources in supercomputing to really get the accuracy on the results.
Okay. Just a reminder again, we still have the questions coming in, but we are getting closer and closer towards the end of the webcast. I hope we can get through all questions, but if you have any other burning question, or if you anything really important that you wanted to know, this is your last chance. Type in your questions on menti.com or on the comment box on YouTube. This is your chance. Get in your final questions. And just summarizing, maybe here's a question. If you're new to the software, can you just remind us all, how can I get going on UltraFluidX for my vehicle? How do I start?
Okay, that's a good point. So first of all, you get your cut parts and get into the Inspire and check them, create a surface mesh, and then you're ready to use to smooth translate to virtual wind tunnel. When you are in virtual wind tunnel, you then easily import these files, the surface STL mesh, and then you have these ribbons in the top where you can then easily start to run or to set up your simulation. Maybe we could have another small presentation here from my desktop to show you guys what it's all about. So we're now at the stage where we imported the settings or the geometry files from here. Now this whole ribbons bar up here is formed streamwise. So if we start right at the front and continue working every ribbon to the ribbon, then we're ending up with the full simulation set it up and ready to run. So first of all, you should definitely look back into the guides, what sizes and dimensions of tunnels and refinements you should use or could start to iterate from. Or you just do it like you want and use the default values virtual wind tunnel also handles in here. And then you continue and then run your simulation. Maybe it's good to start another, a little bit finer one and also a little bit coarser one, and then see if you can determine a difference in those cases. Then you should definitely take the computational power into account and see what's the best setup for you.
Okay. Another question here, how did you get the dimensions for your computational domain?
The dimensions I choose are based on my own experience. I was working on a bachelor thesis with ultrafluidics, so I have a few, I would say already a few years experience in using ultrafluidics. I think that were kind of the first steps where Altair Altair published one of the first ultrafluidics version. I was already on there and then started to iterate. And in my bachelor thesis, I made a big analysis of a Formula student vehicle by using ultrafluidics. I had around 6 or 7 simulations, which I compared in comparison to the wind tunnel results as well. Was a kind of validation and test examples thesis. So in the end, we developed the nearly perfect, I would say, a setup in my case, or my opinion.
Yeah. And another question to build on this, why didn't you have the domain along the longitudinal axis?
What? Okay, that's an interesting question, because normally the air flow should coming up from the front, in front of the car, and going through the whole domain and entering behind the car. So in this case, when we're speaking about cornering situations, then the airflow would come for the side. We just took a normal road track, what is it called, cruising section here to simulate and to have a look at. Therefore, the options we choose, I think they are quite useful to have. But if you want to have crosswinds, of course, then you have to change the inflow.
Okay. Another area, again, what is the benefit of transient simulations as opposed to time average steady state sim?
That's a lovely question. The main goal is that what we will see right now coming up on the screen, where I put back on the slide, where we had the transient simulation or the transient result in detail. So these animations, I think they are already saying quite a lot, and those can't be done by using steady state results. Mainly, you have the opportunity with these transient results to really gather all transient effects which will be lost by using a steady state simulation. Imagine you have a pressure in one time step which is positive and the next time step which is negative. And then it's fluctuating and iterating even back and forth all the time. Then, when it's perfectly even, you wouldn't see this pressure in the steady state result, because the average then, of course, is 0. And these transient results, you see all. In the lower custom case, you see all the fluctuations from that lookout thing, like fluctuating through the fluid downstreams. And this is really what you get then.
Okay, thank you. Thank you, Paul. And last couple of questions that we have here. So if you get one in very quickly, we might be still able to ask them, but last couple of one. Can you compare the accuracy of this program with other CFD softwares like ANSYS Fluent, always assuming identical settings and setup?
You're talking about some benchmarks, right? Therefore, I would say please get in contact with us. I can display the slide again. Go on Altair University at altair.com. May there are some benchmarks available. Just get in contact. Right now, the big advantage I can point out is in regarding of time. I don't know any other program what I used where transient simulations are determined that fast with these awesome results.
Okay, so get in touch, find out more. And again, a question here, maybe taking the result ahead is how much drag reduction can I expect when removing the two side mirrors of a car?
Wow. Okay. Now you get really detailed. So if you remove the side mirrors of a car, when we're talking about a passenger car, it would roughly be 5 to 10 counts. When I say counts, I mean more kind of aerodynamic CFD language thing. It describes that you have one count is equal to 1/1,000. So if we're talking about 5 counts, we say 5/1,000, and 10 counts would be 1/1,000 according to 1%. So I would say maximum drag reduction possible would be 1% of overall drag.
Okay, that's not to be underestimated when you're in a competitive situation. Well, I think this completes our Q&A session. We got through a lot, and we've managed to handle them all, and you managed to handle them all very well. So first of all, thank you very much, Paul, and the whole team at Altair for your time and for these very insightful and helpful presentations. Also, I would like to thank again our participants from Shell Eco Marathon for tuning in and taking part. If you don't have enough yet, there is more virtual learning sessions to come later in May. If you haven't registered for it, please go to our website and register. We'd love to have you to join. And with that being said, I thank you all for your attendance and have a great rest of the day. Bye-bye.
Bye-bye.